Good morning and almost good afternoon, everyone. So my name is Melike Erol-Kantarci. I usually go with Mel to make it simpler. And I've realized that since the time I provided my bio, things changed in my life. So I've been promoted to Strategic Product Manager position at Ericsson, and I'm also a full professor and Canada Research Chair at the University of Ottawa. Now, this might be confusing that I have two hats, and I need to make a disclaimer. I'm here to give a talk about my research at the University of Ottawa. And I would like to talk about towards an AI native 6G and ask the question, is G for generative? Actually, if you're old enough, you would remember the movie V for Vendetta. This is kind of coming from there. And I had started a bit bolder and saying G for generative. And then, with discussions, we started saying, is really G for generative or generative AI more specifically? Now that I'm the last keynote for today, the previous keynotes, Magnus and Paying, very successfully actually prepared the stage for me. They talked about 6G. They talked about AI nativeness. Centimeter wave, I don't have it in my talk, but all of these things are technologies that are preparing us for 6G, so I can be very quick about these parts. I'm going to do a very brief introduction of these fundamental things, fundamental technologies we use in machine learning to make 5G, first of all, AI native, and then 6G AI native. Then I'm going to get to the exciting part, generative AI. It's a very hot topic, and in the telecom world, across all other industries, it's a big discussion on how to use generative AI in a useful way. And by now, I think all of us realize that there's no escape from AI. It's going to be here for some time, and that's why it's good to have this discussion now. Now, before I get into the technical parts of my talk, I thought I should introduce my university and myself a little bit for those of you who are not familiar to Canada. So University of Ottawa is a bilingual university. It's located in the capital of Canada, which is not Toronto, it's Ottawa. And according to the Times Higher Education, we are ranked 8th in Canada and 177 in the world in 2024. For this year's ranking, actually, we have gone a little bit up, but I don't have the THE numbers yet. We are a fairly large university with big numbers of enrollments. And I get often asked about my Canada Research Chair position as well, because this is pretty unique to Canada. So that's why I thought I should probably have a few lines of explanation for that one as well. So Canada Research Chair is a program supported by the Canadian government since 2000. It gives some funding to the universities to basically relieve professors from their teaching loads. And they also provide some research funding for research-intensive professors. It's a very selective program, of course, but it has been executed pretty successfully in Canada. Now, I told you at the beginning that my life is easier because the previous keynotes already explained 6G, the use cases. Now I'll just say maybe one sentence. Why do we need AI? Because with 5G advanced and 6G, we have growing complexity in the network. And we have seen by now that AI can make us benefit a lot in reducing the complexity. Of course, there are concerns that you need computation, energy efficiency of AI, etc. But if we find a way to tackle those challenges, it can actually be a very beneficial tool. And then maybe to solidify things a little bit, when we say AI and 6G or AI and 5G, what are we really talking about? So this is just to give you an example of some of the network functions that can benefit from AI. This is not an exhaustive list, and with my research group, we had almost in all of these areas 1 or 2 papers exploring into applying machine learning techniques. So resource allocation, a very fundamental wireless communication problem, carrier aggregation, handover optimization, energy efficiency of the RAN, network slicing, task offloading in the edge computing environment, reconfigurable intelligence surfaces, which has been a hot topic for some time, traffic steering, beam management, and intelligence orchestration in ORAN. These are just some examples where we have been applying AI into these functions. And when we say AI, actually AI is sort of a very abstract word. And the science of AI started many decades ago, and when it started, the goal was to reach human intelligence. But then researchers at the time realized that it's not an easy task to reach human intelligence, so we started calling the subdomain machine learning. So when I say AI, I'm actually talking about machine learning. And among the machine learning techniques, the field actually exploded a lot. It started with expert systems, and then moved into combining neural networks, into robotics, reinforcement learning, from reinforcement learning, generative networks, from their large language models. I'm going to give a little bit of glimpse of each of these machine learning areas in my talk in continuation, but if we just want to make a small, again, short list of machine learning techniques, they are, let's try the pointer. I like trying new things. Okay. So the right-hand side, you see the machine learning techniques as we apply to the left-hand side control algorithms in the RAN. So without further ado, let's start with those techniques and just maybe in a few minutes go through them because I really want to get to the GenAI part of this talk. And I'm going to follow a chronological order. So you might ask, what's the order of these machine learning techniques? It's the chronological order that we apply these techniques in our research. So we started with reinforcement learning. And the beauty of reinforcement learning comes from this. It's a very old technique, by the way. I mean, it's not by any means new. It has been in the machine learning domain for many, many years. So we said robots or chess-playing machines can learn by iterative action, so taking some action, seeing the consequence, getting a reward or a penalty from the system, they can train themselves. So we said, maybe the algorithms that are running on these base stations, basically network functions, can benefit because these are actually control problems, and reinforcement learning has been successfully applied to control in robotics and in other fields as well. And the interesting thing about this technique is, in the good old days of machine learning, maybe very early days, the researchers was thinking if you were able to teach everything, every rule to a machine, they would become intelligent. But then soon after, it was realized that human intelligence is not really like that. We experiment. We play around, we learn from our experiences, and then that's how we learn things. That was good for some control problems. But then if you have a control problem with limited state and action pairs, you're good. You can be safe with Q-learning, which is a type of reinforcement learning. But if you get into more complex control problems and your state and action pairs increase, that's what we call curse of dimensionality, then you got a problem. Researchers in 2015, Google DeepMind researchers, they have found actually a nice way of integrating neural networks with reinforcement learning, and this was called deep reinforcement learning. So what we do is, instead of storing a table in Q-learning, we have a function approximator, and this is a filter. It could be anything, but they have used neural networks. They could have used one single neural network, and I'm imagining that they started by using a single neural network, but then they had stability issues. Then they came up using 2 neural networks, main network and target neural network. One would store the stable version of the network, and the other one would do the continuous updates. So we have used this successfully in our research. But then we started thinking, there was something that wasn't really right with this, because each time we ran these algorithms, they were learning things from scratch. And humans don't learn things from scratch. We use our past experiences, or we use our experiences from our peers. There is a very nice learning thing, I would say, for humans that scientists haven't been able to solve up until now. But transfer learning is the capability, one of the nice capabilities that we have as humans. So we said, okay, if we have the capability of learning the actions in one domain and then replicating them on a different set of actions, then maybe we could do transfer learning. And we are not the inventors of transfer learning, by the way. Transfer learning was there in the machine learning field that has been used in pattern recognition and computer vision. So you have one data set, you train a neural network, you take the same trained neural network, you put your other data sets that are similar, then you get the outputs in a much faster way. But then our problem was a bit different. We were looking into control problems in the RAN algorithms, so we said we have to have transfer reinforcement learning. So we went to the robotics literature, and our colleagues at University of Alberta had actually applied transfer reinforcement learning for robotics. And we said, why don't we do this for base stations? The first problem we started looking at, actually, that was the time 2021. And we came out with a technique in our paper, transfer reinforcement learning for 5G and our millimeter wave networks. And over there, we were simply transferring some information from the expert base station to the learner base station. And that information, it really depends on actually what you're doing. If you're doing resource allocation in a certain band with the expert base station, then you could learn the resource allocation in a different band. But if you're, for instance, learning resource allocation in one base station and trying to do traffic steering, for instance, in a different base station, then you can't actually transfer this. So the closeness of the actions, replicability of the actions is important. And I mean, it shouldn't surprise you, right? I mean, it's how humans do it as well. I mean, you don't really replicate everything in your life. Our learning applies, like if you're learning things in a classroom for a certain particular specialization, you get very focused, you learn the things over there, but then you go to your daily life driving a car. It's a certainly different skill set, different learning, and then you have a different mechanism for that. Let me move this one more. We decided that, okay, you know, this type of transfer reinforcement learning is nice. We have one expert base station, one learner base station, but it was still not very satisfying to us because humans learn a bit different way. And being a university professor, I said, I mean, the way that we teach is, you know, students come to a classroom in a college. They learn from the professors, but they also learn from the peers, from their friends. So we said, can we do multiple expert, multiple learner systems? And that we applied to a network slicing problem. Over there, of course, then we realized there are actually two possibilities. You could transfer the Q values in the Q learning mechanism from the deep reinforcement learning, or you could transfer the actions. Then, diving into this research, we realize it's not as simple. You have to, just like I said in the previously, like driving skills and learning a specialization at school are different. The same thing applied here. You couldn't actually transfer actions that are not closely related. But then how do you understand actions are closely related? So we looked into the action distributions. So with that, we experimented with multiple base stations for multiple network slicing scenarios, and we were able to show that our deep transfer reinforcement learning technique could get better performance, plus it would converge faster. Actually, that was the main idea. We wanted to have something that we could train faster. Then again, chronologically moving in our research line, that was all good. And actually, this is something inspired me when I was interacting with the researchers at the Vector Institute in Toronto. I'm a faculty affiliate at the Institute, and Vector Institute is one of the 3 AI institutes in Canada. We have one in Montreal run by Yeshua Bengio, the other one in Alberta by Richard Sutton, and the third one, Vector Institute in Toronto by Jeffrey Hinton. So we were having some sort of a workshop there, and I was listening to the robotics professors. They were talking about planning actions of robots, which made a lot of sense. You know, you have a robot, you ask your robot to fetch a cup of coffee to you from the kitchen. The first thing is the robot has to exit the room. It has to go upstairs to the kitchen, maybe fill up the mug. All these things have to be planned. So actually there's a hierarchical thinking behind it. And this is sometimes called goal-oriented planning or hierarchical reinforcement learning. And we said, okay, that might be a good idea for applying into wireless communications because we have multiple controls and multiple timescales. And I'm going to give an example, actually. Maybe I should move into that example to relate it to our wireless world. So we have in this paper that we had presented in 2022 GlobeCom, we have hybrid deployment, macro cell base stations, small cell base stations, and RIS, reconfigurable intelligent surface. What we're trying to do is we're trying to control the sleep schedules of the small cell base stations, and at the same time we have to decide on the power control of the small cell base stations so that they can save energy, and then RIS control, the phase shift control of the RIS element for capacity increase and also preventing blockages. Now, when we were looking into this problem, every problem brings a challenge, and then you solve the challenge, then you have a new, invention or a new paper. So as researchers, we like challenges, and we found out that actually it wasn't as simple again. No surprises. So if we have a meta controller at the higher level, which controls actions at above, let's say, minutes level, like a sleep control schedule, because you can't really sleep the base stations every seconds and then wake them up, sleep them, wake them up. It has to be in the order of maybe minutes, maybe hours, and so on. And then in the lower level controllers, you have to be very fast. It's in the order of milliseconds, and this is where you control the transmission power or the phase shift of the RIS element. But the challenge here was that the feedback from the subcontrollers were varying because they are also doing machine learning, so they are trying some actions, they're getting different feedback, and then they're giving this feedback to the meta controller, and meta controller was getting crazy. We said, no, this is not how you control a system. So we have to have a mechanism to first maintain the collaboration between the subcontrollers. They stabilize themselves. But then even if when they provide unstable feedback to the meta controller, we should have a way to check the cross entropy of the policies and decide which one to go. I will not get into the details of these formulations here, but basically what we did was we checked the Kullback-Leibler distance between two distributions. If the distributions are similar enough, then we take it as we have a similar system, and then we can apply these policies at the meta-controller level. Now, having said this, and I'm checking the time, which gives me actually enough time to go through the material that I have for generative AI. I think, now we have 6G. For 6G, we have growing complexity. I think I was able to convince, with the help of the previous talks as well, that we need AI, we need AI nativeness. Then let's see if I can convince you about the generative AI part of things. A bit of history timeline, again, coming up from the traditional machine learning techniques, traditional statistical machine learning models like decision trees, random forest, support vector machines, putting in the timeline as we begin. We move into neural networks from the machine learning or AI world. No need to define those, of course. But then a little bit further into the time, we started seeing generative AI models actually coming. So these ones are actually, I'm not talking about the large language models. These are a little bit before in time. And these are generative adversarial networks, variational autoencoders, and transformers. And in combination of neural networks, all the research in that domain and the generative AI domain resulted in the large language models to explode by the end of 2022. It became a big thing. The industry got excited, the society got excited, and the main reasons that the society got excited was because for the first time we could actually play with an AI tool. We had the ChatGPT, we could type prompts, get answers, and from there on, of course, we also in our research lab tried to see if we can use it in a useful way for our research. There are many large language models. I'm not going to talk about all of them. Just in this slide, we have GPT, Llama, and Phi just as an example, but it's a huge space. And then the question is, can we get into artificially general intelligence? It looks like the field is moving very fast. It's hard to predict what's going to happen, but it's just likely to say that there will be very big advances in this areas. There will be, of course, regulations around it. And all of us in the technology and research area, we need to see how we can contribute to this space. Again, moving in the timeline, the end of 2022, ChatGPT came out, and we all started experimenting. In 23, that was a big topic. So in the research community, people started looking at how we can apply large language models or generative AI to the telecom domain. I listed 3 references from several of the researchers. I know some of them are in this room. I can recognize some of the names. And the first paper talks about, actually makes a comprehensive review of the deep generation models and how they are applied to wireless networks. And the first works always, start as tutorial or more survey-like papers, but then we see more implementation type of papers. The second one, again, coming from one of the prominent research groups in this area, and it was about introducing ways of integrating large language models to the telecom domain, and there are several innovative ideas in that work. And number 3 is a more recent one, and it discusses it actually proposes a general model for the generative AI empowered network layer, so introducing a different layer to enhance the performance of communications, again, another innovative research work from the community. Then the next 3 ones are actually the ones that I'm going to talk about in the next slides, and these are from my research group. I'm looking around to see if I can spot my PhD student who actually traveled with me and who is the author and the inventor of many of these works. But Han, if you are around, you can just stand up and wave your hand so that I can direct the difficult questions to you and I take the easy ones. But yeah, as you can see, all of these references are quite recent, 2024. These are the papers we submitted for publication. They are patent pending, all very hot off the press papers, I can say. The first one will talk about how we can integrate generative AI into the human and machine learning principles. The second one will talk about a bit on a specific application of a large language model tool for network intrusion detection. And the third one, actually I have a fourth one which I didn't put here because it was going to be too crowded, but I have it in the slides. The third one, the last one, goes into actually the Isaac concept that we were able to reproduce LiDAR data by using only camera and radar image data. So it's actually very, very powerful. You will see that these are opening up really very interesting opportunities that even when we started our research, we didn't think we could reach these, but they were quite impressive. The results were quite impressive. So the first work that I want to talk about is bringing generative AI in the loop, because both in the industry and the academia for telecom, there is a concern whether, generative AI is reliable or we can leave the whole control to the generative AI. This was a little bit towards addressing this concern. So we came up with a view that we say all of these domains, traditional machine learning algorithms, large language models, and the humans, as we see those 3 categories over here, they have their own strengths. And we can use large language models to consume much more data and act as an intermediary in between for controlling the intelligence. So we're not giving away on our AI native control loops. Our machine learning algorithms can still work in the RAN. But How we coordinate them, we can do the coordination by using large language models because they are able to consume multimodal data from the RAN environment. They can see the environment. They can see all those buildings, see the interference, get all this information with the mobility and everything. And machine learning models would combine them with the data that they collect from the networks. And then we have the humans at a certainly different but a very important level that they have the expert knowledge. They have the understanding of the system and the big picture, and they can handle complex or unseen conditions. Now, I know this was a little bit abstract, so that's why I included our second work, which actually gives you a very good example of how we combine a large language model tool with network intrusion detection. So we start with a labeled data set. With the labeled data set, we list and index the features, and we identify which features are important for us. So you can consider it like doing PCA with a large language model, principal component analysis. The large language model can identify which are the important features, so it lists them and gives the indication. Next, we start monitoring the network. When we monitor the network, we monitor based on the importance of these features. So the important features that have been identified in the labeled set are now being monitored first in the unlabeled data set, and they are fed into prompt generation. I'm sure many of you have heard about the concept of prompt engineering. Actually, that's what we did in our paper. We use a technique that's called in-context learning. And if you have experimented with these tools, I'm sure you know it. The more accurate inputs or the more accurate questions you give those chat tools, the more accurate answers you give. So we tried to give, okay, this is the IP address and the source port and maybe other parameters that we identified as threats to the network previously. Now we're getting this information from the network. Do you think it's an intrusion or not? Give me an answer, yes or no. You have to be very explicit with these models. Maybe in the future it will change as well, but for now that is the case. And then we have the step 4 as decision extraction. Just to exemplify this, you have this table with a simplified version, of course, with source IP, destination IP, flow duration, ports, etc. Then we have the prompt giving that now you have observed this information, and we give several examples, in-context examples, and then we give the test example, tell me what you think about this, whether this is an intrusion or not. And we've been able to show that with ChatGPT-4. We get a really good performance, especially if we provide close to 10 in-context examples, and this is not a huge number, frankly. We could get a twice better performance in intrusion detection. So that was kind of a result that got us excited a lot. Now, the other work that I wanted to talk about today is, again, something we recently submitted, also filed a patent on, is synthesizing LiDAR data by using different sources of information. The sources of information, we are using a data set that's provided by one of our colleagues from ASU. It's called the DeepSense 6G data set. It has radar, camera, and LiDAR images, but LiDAR sensor is expensive. So we said, can we find a way to replacing LiDAR sensors? So in the future, if we get into the concept of JSAC or ASAC, joint sensing and communications, or integrated sensing and communications, can we have a system that we don't need a LiDAR sensor? And we were able to collect the point cloud sensing data. We were able to generate the point cloud sensing data of LiDAR by only using 2 modalities. Now, this is the last work that I have, then I will wrap up, and let me check how I'm doing with the time. So with this work, actually again another recent one, we combined intent management or intent handling with large language models. Now of course this is a concept of its own. It might take some time to explain, but very briefly, what we mean by intent is the operator's intent of managing their networks. So it could be something like reduce my energy consumption by 10% during this and that time, but maximize my throughput to such and such values. So these are actually very, human-like, these are language expressions, basically, that we can use large language models to, again, understand. And in this work, particularly, we were using the BERT language model. Well, actually, we used a lightweight version of BERT. It's called Albert. And we looked at the intent of the operator. The next thing after understanding the intent is intent validation. Can the network actually satisfy the intent? To be able to do that, we used our previously proposed transformer-based traffic prediction technique, and we monitored the network traffic. So by monitoring the network traffic, we were able to validate whether an intent of the operator can be satisfied or not. If an intent can't be satisfied, it's not the end of the world, we could still do network optimization. So the third step that we have here is the network optimization, and it gets into that part. So by using our network functions, traffic steering, beam management, energy efficiency in a coordinated way, we were able to reorganize the network, again by the help of an attention-based transformer mechanism, and we were able to improve the performance. Like over here in the charts that you see, there's a performance degradation because of an unvalidated intent, or there's a possibility of performance degradation, but by coordination, we're able to fix it. Now, hopefully, I was able to get you a little bit excited about the generative AI technology, but as an academic, I have to give you the full view, full picture of things, that it's not a fully ready, mature technology. There are things that we still need to do research on in order to make this technology safely, securely, reliably used in the telecom domain and in other sectors as well. But basically, the key takeaways are we all know by now that AI will play a significant role in 6G. It's already playing a role in 5G and 5G advanced. Generative AI is in its infancy, but it's growing fast. And one very important aspect of this technology, in my opinion, that AI has never been as close as this to the public. So now we can play around with it. It is a part of our lives. So being this in our personal lives, the ability to apply the technology gives the appetite to the industry to adopt it in various ways. We know that generative AI will drive new services. Maybe it's going to be the next killer app or the killer apps, a series or serial killer app for the 6G. But then it has problems. We have hallucinations. Lack of high quality of data. We know with machine learning it's always garbage in, garbage out. So the quality of data that you provide to these large language models or multimodal models is quite important. A lot of the large language models are larger in size with billions of parameters, but by now we know that we can have smaller models, but they can be still relatively large for fast control actions. The bottom line is we need more research, more activity in this field to make the next G GenAI enabled, powered, or maybe even GenAI native, and time will show us. Now, finally, of course, this research is not possible with the effort of our students. Many thanks to my past and current PhD, master students, as well as postdocs, and also generous funding that we have received both from US and Canada. Thank you very much.